Ah, didn't see you there. Just been reading some biogeography. Excellent topic. Highly recommend it. But you're not here to talk about that, are you? No. You want to hear my opinions on should we abolish the P-value? Well, let me begin. The P-value is one of the most used and misused statistical tests, and there's confusion between statistical significance and practical importance. The controversy surrounding it has become more prevalent in the past 10 years, with experiments such as demonstrating that a significant P-value can be obtained from data noise and failing to replicate published results. Let's get back to it. So what is the P-value and what does it signify? The P-value is a given probability that an event, like a scientific experiment, occurred through chance. It measures the odds of no effect occurring, the null hypothesis, and the smaller the P-value, the more unlikely the null is. An experiment is deemed significant or important if the P-value is less than 0.5, and if it is less than 0.001, it is deemed very significant. But is that what it's telling us? Well, no. All it shows is that there was a 1 in 20 or 1 in 1,000 chance that the experimental data collected occurred through chance. So where did these values come from? The P-value was first introduced by Carl Pearson in 1900, and in 1925 Sir Ronald Fisher created a common way to calculate it. It was originally meant to judge data to determine whether it was worth further study, not as a definitive test. But there must be some problems with the P-value. It is open to abuse. The problem of P-hacking occurs when someone unduly influences data collection processes or statistical analysis performed in order to produce a statistically significant result. A good man once said, "When a measure becomes a target, it is no longer a measure." Goodhart's law. This can also happen if some data is left out deliberately in order to force a statistical significant result to occur. Hazards associated with this are the likelihood of false positives, findings that the statistics suggest are meaningful when they are not. Here's an example of P-hacking and the problems it can cause. Here in this graph, there's clearly a correlation between the best word in a spelling bee competition and the number of people in the USA killed by venomous spiders. So what does this show us? Nothing, because it's a load of The relentless quest for a significant P-value is only one of the many problems with data analysis that can contribute to the reproducibility problem. For example, a team at Bayer Healthcare reported in Nature that when they tried to replicate 67 published studies, of those 67, only 14 were able to be replicated. Papers should be tested by other scientists to try and replicate the results to ensure that discoveries are as they are meant to be. However, replication costs money, which is not always available, and this type of research is less prestigious than the original research, therefore journals tend not to publish these studies. There are of course positives of using P-values. They're fairly simple to use and understand, and allow for critical decision making based on evidence through testing hypotheses of different statements or data. They are of course important as they can not only measure consistency of results, but they can also show if data conflicts with statistical models, whilst also outlining inconsistencies between different sets of data. P-values also provide a clear distinction between experimental evidence and inferential conclusions, while also providing a foundation for combining the prior evidence with the current evidence. Yes. Alternatives to the P-value. A key information criterion gives a collection of models for the data. AIC estimates the quality of each model relative to each other model. Thus, AIC provides a mean for model selection. When a statistical model is used to represent the processes that generated the data, the representation will almost never be exact, so some information will be lost by using the model to represent the process. AIC estimates the relative amount of information lost by a given model. The less information the model loses, the higher the quality of that model. This benefits as it compares models and not data sets. However, it is more niche and must be adapted for a smaller sample size. Bayes' theorem describes the probability of an event based on the knowledge of conditions that might be related to that event. This means that after carrying out preliminary investigations, you can guess the probability of certain outcomes. This is good as it's not influenced by data or sample sizes and can deal with unknown parameters. However, like the p-value, Bayes' factor alone are insufficient for inferential statistics because they only quantify the relative evidence in favour of two competing hypotheses. Well, to conclude, it's clear that even though the p-value is a fundamental and widely used function in statistical analysis, it can be hugely problematic and easily misconceived when interpreting data. This has led to confusion and controversy regarding the place of the p-value in statistical analysis. Instead, we can use various alternatives as previously mentioned: a key information criterion, Bayes' theorem. The debate over p-values is important as it drives for change and helps us move away from corrupt scientific research, so we can hopefully see fewer false positives and more accurate publishings in the future. Well, what a journey it's been. We learned a lot today about the p-value, didn't we all? Anyway, I best get back to my biogeography. Wow.